Duhamel's principle is a formalization of the idea that you can often trade off initial conditions for forcing terms. So let's see how this works. So suppose we've got a standard harmonic oscillator. So my double prime plus cy prime plus ky equals, and we'll start it, we'll look at the homogeneous case, and we'll start it at equilibrium, and we'll start it with an initial velocity, say 1. And so this is, think about a pendulum, and we'll start it in equilibrium like this, but with an initial condition of a positive velocity. So what is that? Well, you're suddenly going to make it go forward at time 0, right? Okay. Well, this is the same thing as looking at the situation where we give it a smack at time 0. So we start it at rest in equilibrium, and then at time 0, we hit it with a unit impulse. So, and maybe just to make sure I've got everything lining up right, let's take the mass of our pendulum to be equal to 1. Okay, so then it turns out that the resulting equations of motion for these two are exactly the same, as you might imagine, and it can be shown fairly easily with Laplace transforms. So let's extend this idea. So suppose we have y prime plus ay equals 0. So now just looking at a first order initial value problem, and we'll take y of 0 to be, and we'll specify what we want for our initial value. Now this is the equation for a standard population growth model, or actually rather a decay model. And so you solve this one and you find that y looks like constant times e to the minus at, and then using the initial conditions we find out, so let's evaluate, and we get ce to the 0, so that we have c is equal to f naught, and you know that the solution then is going to be f naught e to the minus at. Alright, so let's modify this problem a little bit, and now consider y prime plus ay equals 0. This time, instead of starting it at time 0, we'll start it at some time in the future. Let's call it tau. And the value that we're going to start it with, our initial population or whatever, is going to be f sub tau, let's call it. Okay. Then once again, you find that y is equal to ce to the minus at. And when you use the initial conditions, you find that f tau is equal to ce to the minus a tau. So this time your c looks like ea tau f sub tau. Okay, so our solution is f sub tau, and then combining the e to the a tau with the e to the minus at, we have e to the minus a t minus tau. Okay, so this looks like we've shifted things forward in time, right? Okay, so then for a final point of comparison, consider if we had y prime plus ay equals Dirac delta located at time tau and coming in with magnitude or force f tau. Okay, so then now this one is no longer separable, so you'd have to solve it using an integrating factor. So you have e to the at y, or the left side would be the derivative of e to the at times y. So when we integrate, it's going to be, and so here we've got our integrating factor e to the a, and I guess I need some other dummy variable because t is already in use, so I'll just call it s. And we have delta tau s, and this number f tau ds. And then if I multiply the e to the at over to the other side to solve for y, well, I can put that inside the integral. Even though there's a t in the upper bound, it's fine because I'm integrating with respect to s, so I can stick it inside and I'm not violating anything. So then this is going to look like integral of e to the minus a t minus t minus s, because we're inside the integral, and then delta tau of s, and f can go anywhere, but I'll stick it inside the integral, why not? So we have this one. And then let's see, so how does this boil down? Well, when I integrate, or when I do that integral, I use the power or definition of the Dirac delta to say that it's going to evaluate this integrand precisely at the point where s is equal to tau. So that s is going to become a tau right there. And so this becomes e to the minus a t minus tau, and then I've still got that constant f of tau. But this only happens in the case when tau is in this interval from 0 to t. In other words, when you're integrating over that. So this is for t greater than tau. For t less than tau, you get nothing. And so this is actually the same thing as e to the minus a t minus tau f of tau times the unit step function based at tau. So here this is, I'm just going to draw a little picture of the unit step function that I mean. It is this one. So this is u of tau, because this over here is 0 and this point here is tau. So that's the function that I'm looking at. And now if we're being totally honest and we go back to the example we did just before this, if I'm starting this thing with an initial condition at time tau, then presumably I'm assuming that actually nothing's going on prior to time tau. So in fact, I should do the same thing over here and include my little cutoff function and say, okay, so this is actually going to be times u sub tau right here as well. And now you see these two things match. Additionally, I should probably be thinking of this initial condition right here as saying, well, so apparently the nothing was going on, and then I actually added f of tau at that time. So I want to think of this initial condition as something that was added to the system at that moment in time. So let's see. So now what happens if I want to add something at more than one moment in time? So I'm going to say, what if at time 1, or tau 1, I'm going to add in some amount of stuff, and then at time some other point in time I'm going to add in more stuff. So whatever, some f sub tau 2 is just the amount of stuff I throw in at tau 2. Okay. So now what are we going to get? Well, our resulting solution is going to look like f tau 1 e to the minus at minus tau 1 with a cutoff function activating at time tau 1, and the same thing at the next time something happens. So I have this guy. And so now if the time is past tau 2 so that they're both turned on, so if this is for t greater than tau 2, then this is going to look like a couple of constants that have been evolved forward in time or decayed by an amount t. And so here those constants, those are actually given by just what they need to be. And then you can repeat like the whole thing and say, well, what if I throw in little bits of extra force at a bunch of different times? Then all these things are going to be stacking up and each get turned on at the appropriate time tau I. And so on and so forth, right? So this is when I'm adding little discrete amounts of stuff at each time tau sub I. And so then you could say, well, what if I just add stuff continually? So now f is going to be a continuous function, and we actually end up looking at the the non-homogeneous version. So what happens now? Well, like we did before in the example with the Dirac delta, we're going to need to use an integrating factor, multiply across both sides. And so this would be e to the at. Now this is f of t, and we have some constant. But we can rewrite that also as the integral from 0 to t e to the a tau f of tau d tau. So the first one is written as an indefinite integral with an arbitrary constant. The second one is written as a definite integral. They're both valid. The first one's a little more common in the US, but the second one shows things a little bit more explicitly in terms of the parameters. So then, once again, we can solve by bringing the e to the at to the other side. And so we get that y looks like integral from 0 to t e to the minus a t minus tau f of tau d tau. And so what I want you to do, aside from noticing the commonality between the one above and the one below, is think about this as saying this is the cumulated effects of adding f of tau to the system at time tau, so that the amount that it is evolved forward by the decay equation is given by this this whole expression. So I tried to draw a picture of this. I don't know how successful this is, so bear with me. But here's my picture. And so the idea is that so we start off at time 0, and there's f of 0 is how much is given. Under this equation, what happens when you evolve forward in time is it decays. So here's the decay curve moving with time. This diagonal line here is the line t equals tau. So at tau 1, when we drop in another bit of interesting stuff, force, whatever, or like additional decaying radioactive material, then what happens? Well, we're going to put it out here because we're going to drop it at time tau 1, and then it's going to decay as well. But it's going to add to whatever we had before. So this quantity right here is y of tau 1, this area. And then I know I'm sort of mixing between a discrete and a continuous picture, but just sort of bear with me. And if we look out at some other distinguished time tau 2 in the future, then it's going to get introduced over here, and it's at height f of sub tau 2, and it begins to decay, blah, blah, blah. And now the amount that we're considering is going to be whatever's including all of this stuff right here. So in the case when you have this continuous distribution of this, which is this your forcing function, then this gets dropped in continuously on, and this is some curve that's supposed to be over the line t equals tau right here. And now we really are picking up these areas for each slice. And if you look really closely, you can see the unit step functions that are coming in So there's one right here, and then it's being modified, so it's the unit step times the decaying exponential, which has been shifted forward in time, and so forth. So there's here's another one. There's the decaying exponential turns on, or sorry, the unit step function turns on right here, and then you have a decaying exponential with magnitude f sub tau 2.